You know, every single day, we're all navigating this world built on a language we never actually see. It's spoken by machines, like in the blink of an eye. So today, we're going to tell the story of that language, the secret protocol that's behind basically everything you do online.
I mean, think about it. It seems so simple, right? You click a link and boom, a web page just appears. But in that tiny fraction of a second, your request is literally zipping across this huge global maze of networks. So how in the world does it know where to go? Well, that's exactly the question we're diving into today.
All right, so here's our game plan. We're going to start with the internet's secret language itself. Then we'll look at how networks can speak in different dialects. After that, we'll see how engineers write the rulebook to get them on the same page. We'll explore how the best path is chosen, and finally, we'll touch on how we can make those routes even smarter for a faster internet for all of us. Let's get into it.
Okay, so let's jump right in. To really get how the internet works, the first thing you have to wrap your head around is that, well, it isn't one single thing. See, the internet is really this gigantic collection of thousands and thousands of independent networks. We call them autonomous systems, or just AS for short. Now, the best way to picture this is to think of each AS as its own country on a global map. So your internet provider, that's one country. A huge tech company, that's another country. Even a university can be its own country on this map.
So you've got all these different countries, right? How do they talk to each other? How do they exchange, mail, or in this case, data? Well, they all use a common postal service, and that postal service has a name, BGP, which stands for Border Gateway Protocol. You can think of it as the official GPS of the internet. It's constantly sharing maps and directions, so a little packet of data from one country knows exactly how to get to any other country on the planet.
Okay, now for part two. And this is where things start to get, well, complicated. See, everyone agrees to use BGP. It's the common language. But what happens when they all speak it with a different accent or a completely different dialect? This isn't just a hypothetical. It's a massive challenge in the real world.
So let's follow our little data packet on its journey. Imagine it arrives at a border crossing between two of these autonomous systems. On one side of the border, the network is running on equipment from Nokia. On the other side, it's all Cisco. This is an incredibly common setup, by the way.
Now, both of these systems, Nokia and Cisco, they speak BGP just fine. But, and this is a big but, they do it with their own unique dialects. Their core philosophies, how they're designed, and how they show you information are just different. And these seemingly small differences can lead to some major confusion for the people running the networks.
So, let's put ourselves in the shoes of a network engineer. They're looking at something called the Routing Information Base, the RIB. Just think of it as the device's map of the entire internet. Now, if you're on a Cisco device, that map shows you everything. Every single path it learned from its neighbors, plus all the paths it created on its own. It's all right there. Total transparency. But then you switch over to a Nokia device, and its approach is totally different. Its main map only shows you the paths it's received from other networks. Its own local routes, they're tucked away in what you could call a separate folder. You can see how this would be maddening, right? An engineer could waste hours trying to find a route that seems to be missing when really it was there the whole time, just in a different spot.
And believe me, this isn't some academic problem. We're actually pulling from the real-world experience of a network expert named Anton Karneliuk, and he puts it pretty bluntly. This kind of philosophical difference is exactly what makes an engineer go crazy when they're trying to fix something in the middle of the night.
Okay, section 3, writing the rulebook. So, you have all these vendors with their own dialects. How do you stop everything from descending into complete chaos? Well, the answer is engineers create a common rulebook. It's their way of translating and controlling the flow of information right at those network borders.
This rulebook is built using something called route policies. And honestly, the best way to think of them is like customs agents at a border crossing. They inspect every single piece of routing info that tries to get through. They can say, yep, you're good to go, or nope, you're rejected. Or they can even stamp it and modify its details to make sure it follows all the local rules of their network.
And you guessed it, the vendors have different philosophies here too. So with Nokia, it's kind of like having just one customs agent who handles every single type of package. Letters, boxes, you name it. Cisco, on the other hand, gives you more flexibility. It lets you set up different agents for different types of packages. You can have one agent just for the letters and another one just for the boxes. This gives engineers way more granular control, especially when dealing with the two main flavors of internet traffic,
IPv4 and IPv6.
All right, moving on to Section 4. So now the networks can talk to each other, they have their rulebooks in place, so what's next? Well, now BGP has to do its single most important job, looking at all the possible paths a piece of data could take and figuring out which one is the absolute best.
I mean, this is really the heart and soul of BGP. The internet isn't just one road. It's this massive web of overlapping, redundant connections. Your data could probably take dozens, maybe even hundreds of different paths to get where it's going. BGP's whole purpose is to run this super complex decision-making process to pick the single best, most efficient route. And it has to do it pretty much instantly.
So how does BGP keep its map from getting hopelessly cluttered? Because without some kind of organization, a router's map would just be overwhelming. I mean, imagine a map of a city that had to list every single street address instead of just showing you the neighborhoods. That's kind of what we're looking at here, a simplified before picture with a bunch of very specific network addresses.
And now, the after. This is one of BGP's most powerful tricks. It's called aggregation. So instead of listing all those individual street addresses, BGP can just summarize them all under a single zip code. And the result? The routing tables get way, way smaller, which in turn makes the entire internet faster and a whole lot more stable.
So the big question, how does BGP actually pick the best path? Okay, the full process is mind-blowingly complex, but we can boil it down to 3 key rules. Rule number 1, it always follows the local house rules. We call this local preference. If an engineer says, use this path, BGP listens. Rule number 2, if there's a tie, it picks the shortest strip, the path that crosses the fewest of those network countries. And rule number 3, if it's still a tie, it goes with what it knows. It picks the oldest, most stable route it has on file. Simple, but incredibly effective.
Okay, final section. So what happens when BGP's best path isn't actually the best path for what you need to do? Maybe it's not the fastest for gaming or the most reliable for streaming. Well, this is where engineers go from just reading the map to actually redrawing it themselves.
This whole process is called traffic engineering. By tweaking those attributes we talked about, like that local preference, an engineer can basically tell BGP, hey, ignore your usual logic and do what I say. For instance, they can crank up the local preference value to something like 200, forcing all the traffic down a specific path. Maybe that path is a bit more expensive, but if it has way lower latency, that's absolutely critical for things like video calls or online gaming.
But there's an even more powerful tool in the toolbox called BGP communities. The easiest way to think of these is like digital tags or sticky notes that you can attach to a route as it leaves your network. These tags are like little instructions for other networks. They can automatically tell a neighbor, hey, when you see this tag, handle the traffic this specific way. It's like sending a set of automated instructions along with your data, which is a huge deal for managing traffic on a global scale.
And of course, this technology never stands still. The next big thing on the horizon is called segment routing. So if BGP is like the internet's GPS, giving you the best route from A to B, think of segment routing as giving you the power to create a totally custom turn-by-turn route. You can tell your data packet, okay, first go here, then make a stop here, and then go to your final destination. It's a level of precise, programmable control that we've never really had before.
So when you step back and look at it all, you realize the internet isn't this static, fixed thing at all. It's more like a living, breathing map that's constantly being redrawn every single second by these invisible protocols and the brilliant engineers who manage them. Which kind of leaves you with a big question, right? As our tools get more and more powerful, what happens when the map itself starts to think?